In this video, we just want to talk a little bit more about some of the stress analysis. We talked about it at the end of class today. So if we look at link CF and we look at the MATLAB solutions, you can see that at this joint we have 1.88 newtons up and 1.25 newtons to the right. Then down at joint C, we just have the opposite. So this is a two-force body. Using the Pythagorean theorem, we can get the actual magnitude of the force vector, and it's lined up, it's in the direction of the link. And so we took a slice through here and wanted to determine the tensile stress in that section. We need to find the area. It's just 5 millimeters by 10 millimeters. And then if we look at, midway between the two joints, then the tensile stress would just be the force divided by the area. So we just do a conversion from square millimeters to square meters, and we get this 45,000 newtons per square meter, which is a very low stress. But that's a way that we can calculate the tensile stress. And then, of course, if we look at the joints, the holes have a 5 millimeter diameter, so we only have half as much area. So we would expect about 90,000 newtons per square meter. But in reality, we'll look at the FEA in just a minute. The stress is actually, there's some stress concentration around the hole. So it's actually around 120, instead of 90,000, it's around 120,000. So here's the FEA, and we have the load applied here, and you can see that in the middle section here, halfway between the joints, it's around 45,000 newtons per square meter, matches very closely to our calculation. If you get around the hole here, you can see that we'd expect around 9,000, but we have some areas of stress concentration right around the hole, so that actually gets up to around 120,000, which is expected. So anyways, it's always nice to be able to do some manual calculations to try and validate that you're in the right ballpark with the FEA. So now we want to look at a different link. All right, so now we want to look at link HI, and if we look at these values here, let's see. These are the values from MATLAB and also from the SolidWorks motion study. So we have at this joint H, we're looking at link HI. Obviously there's some reactions down here, and we have T2 as well. But we have 0.66 newtons down and then 0.62 newtons to the right. Now when we do the FEA, this part was drawn so that it was horizontal. So we want to get the correct angles here. This is 60 degrees, so it's 60 degrees between this X component and the direction of the link, and 150 degrees to get to the Y. So using those values, we want to break these into components, and this one has a component that's trying to compress the link. The X component has a component, in line with the link that's trying to put it in tension. So those are kind of opposing each other a little bit, but they both have a perpendicular component that's adding to a bending moment here. So that's what this calculation is right here. So in other words, we have 0.66 times cosine of 60. That's this perpendicular component, and then the length of the link, the distance between the joints, is 60 millimeters, or 0.06 meters. And then this other one, 0.62 newtons, multiply that times cosine 30 to get the component from this 0.62 newton force that's perpendicular to the link, and again multiply that by 0.06, and we get 0.052 newton meters. which also agrees with the motion study calculation for T2. So now we have the bending moment. We want to calculate the moment of inertia of the cross section, which is 1/12 pH cubed, and these are in meters, right? 5 millimeters is 0.005 meters. And so now we have the moment of inertia in meters to the fourth, and we can go ahead and use this equation. The C is just going to be 5 millimeters, right? It's the distance from the center up to the top. And we end up with 624,000 newtons per square meter for the bending moment stress. And obviously that's going to be close to this point, down this point right here. So when I did the FEA, I just fixed this one. This would be attached to a shaft that's applying a torque and some load, and then just applied these forces out at the joint. And I also calculated the compressive load. So in other words, just take the components of the 0.66 and the 0.62 forces that are in line with HI. That's where the 0.66 times cosine 30 minus 0.62 times cosine 60. I think this is a compressive force. And that you can see is quite low. It's around 5,000 newtons per square meter, as opposed to the bending moment stress, which is 624,000. So let's look at the SolidWorks simulation now. So here's the SolidWorks simulation. We have the 0.66 Newton load that's at 30 degrees from the horizontal, right? If I click over here, you can see that it turns blue. And then the other one, the 0.62, if I click on that, let's see. Okay, there it goes. That's down at 60 degrees from the horizontal. So we apply those two loads, and then we'll show the von Mises stress here. All right, and we have some stress concentration here, and so if we look up at the top here, we can see the von Mises stress is pretty close. So that would be 527,000. That's reasonably close. And then down near where the hole is, we have some stress where that attaches to the shaft, and you can see that I think we've estimated it was going to be around 640,000 up here, but this again seems well within the ballpark for this type of analysis. So again, to set this up, we fixed this end over here where it connects to the shaft that's applying the torque, and then this is where the load is back on the, move this back up, the SolidWorks. Okay, so here's our sketch again. And again, we estimated the bending moment stress was going to be about 624,000 newtons per square meter. So that seems to be in the ballpark. And so that's, again, an example of calculating the compressive stress and the bending moment stress. So I hope this helps.